Hello, hello. This is the beginning of the recording for Wednesday, April 29th. I almost said February 29th. It is a leap year, but it's definitely not February right now. Yeah, so hope you're doing all right. I yesterday in the afternoon I got this hand cramp using this pen, or maybe that was the day before. The days are some of these things are kind of running into each other, but I had in some lingering hand cramp from using this stylus that I'm not used to, and then I accidentally cut my hand. I mean, lots of. Then I got a headache, I think, from that. I don't know. Yesterday was just one of those days. It wasn't such a bad day, but I sort of lost my rhythm in general. Okay, well, what I'd like to do is there will be announcements at the end, but let me just start with the warm up now. Um, I would do the warm up and then do announcements, except that what the warm up does is going to get in the way. If the, sorry, announcements would get in the way of the next thing that connects so much with the warm up. Please forgive me for that. Um, if you're watching the recording and want announcements, you can scroll to the end of the video for that. Okay, so there are two parts to this, and I kind of compacted how these are written up here. So we had this indefinite integral of 2x dx, and we have this definite integral of 2x dx where x starts at 4 and x ends at 10. So these two, um, that these look so similar, other than there's the 4 and the 10 missing here. And this indefinite integral question, right, this is an antiderivative problem, right? So I want to really clarify and make sure that we don't confuse issues today, especially that when you look at an indefinite integral such as this one, what's the final answer going to be? It is going to end up being a family of functions. Now, I don't maybe worry too much about the phrase family of here. That's just what the plus c is trying to account for. We're trying to find antiderivative. In other words, the derivative, the question here is the derivative. Oh my goodness, the derivative of what thing is 2x, right? That's what the question of an indefinite integral is. And well, here it is. I've done this in some stages. You might just directly jump from here to there. But what I've included is just sort of kind of fitting our principle of the 2 is copied, and then you anti-differentiate x to the 1. You raise the exponent up by 1, so you have an exponent of 2 here, and then you need to divide by 2. You always divide by that new exponent when undoing the power rule. The 2's here cancel, so you're left with x squared plus c. Of course, this one, just because the number is nice, you could have done this one directly. What I mean is, you might just be thinking about what should I differentiate in order to get 2x? And the thing to differentiate to get 2x would be x squared, well, really x squared plus any constant. Okay, that's the indefinite integral. There's the definite integral, which looks totally different, right? So the answer to a definite integral problem is a number. That number represents area, signed area, maybe more specifically, shown in yellow in this picture here. So what you see here is a graph of the function f of x equals 2x that way. You have an x equals 4, that line. I drew it in dotted. It's kind of a little bit easier to see what we're going to be doing next if I drew this dotted. Same deal here, x equals 10 dotted. And I included the y values of 8 and 10, which of course you get by plugging into the function 2x. And I'd like to show how to get this yellow area here for this part 2 question in two different ways. Both ways work. Neither is right, or sorry, they're both right, but neither is like wrong, or one isn't preferred over the other. But intentionally, I'm going to show you the way that I think people tend to naturally think of computing this area is to split this up, right? Like kind of divide this right here, and then you'll have a triangle above and a rectangle below, and that's totally fine. So that's this first one. I didn't mean to reveal both of these at the same time, but I can't change this on the fly. So over here, you can compute this as the area of a triangle. So this triangle happens to have a width of 6 and a height of 12, plus the area of this rectangle in red down here. That's the 6 times 8. And I just wanted to go through the arithmetic of having this 84. Just to point out that if you computed the area a different way, so these colors don't make, why these colors, why the purple and the green, it doesn't make sense yet here. Let me advance the slide forward one. The other way to compute the area that's in yellow the signed area that's shown in yellow, is to compute the I had to get a little creative with colors here, so sorry. Is to look at this big triangle. I've outlined it in the same purplish color. This is what the computer called purple. So this big triangle has a base of 10 and a height of 20, so 1/2 times base times height. But if we only want the region in yellow, we've counted too much. So I've shaded in this green part as saying, well, we don't want, if we only want the region in yellow, the big triangle is too much, and so we have to subtract off that triangle that's shown in green, and that's a 1/2 times and a base of 4 and a height of 8. So there's two ways. One way was to, if I step back a slide, was to look at the blue triangle and the red rectangle and add the two areas together. And then the other way was to look at the big triangle, but that's too much stuff, and then subtract off the triangle that's shaded here in green. Either way works. Just to show that you still get the same number 84, what I did here was I did the 10 times 20 is 200. You don't have to, right? Like in these you could stop here, but I'm just trying to make a point for in class that you get 200 here, you get 32, and then let's even simplify this, right? So half of 200 is 100, half of 32 is 16, and when you do 100 minus 16, you get 84. So you get the same final answer. So what happened here was we did part one, this indefinite integral, and got a function plus c. That's an antiderivative problem. We did the definite integral, which the final answer needs to be a number, and we got that number two different ways. We got 84 as the sum of a triangle above up here and a square down or a rectangle down there, and we also did it this way of the bigger triangle minus the smaller triangle. Okay. So far these two problems don't seem to have any connection to each other. Right, that's so far this notation. Why would these two totally different looking, or sorry, these two problems that have totally different processes at all have any similar notation? That just seems like mean in terms of creating notation that's confusing. Now we're going to connect things together. What I want to do on the next slide is I'm going to copy this. I'm going to actually skip most of this work, and I'm only going to copy what's in bold here. So I'm going to take the work that we did in the indefinite integral on the next slide, as well as integral 4 to 10 of 2x dx equals, and I would suggest you write this down right now, 100 minus 16. So this one, integral 2x dx with no numbers on the integral sign equals x squared plus c, and then integral 4 to 10, 2x dx. I know the final answer is 84, the two ways we did it, but the way I want to focus on it right now, you'll see next slide, is 100 minus 16. So here they are. Okay, so the promise has been we're going to talk about the connection. Why this problem and this problem, even though they have really different, completely different thought processes, does the notation for the question look so similar? Well, it turns out here's another way to write this one. So I'm going to keep the left side, this integral 4 to 10 of 2x dx the same, but I'm going to rewrite 100 minus 16 to make it even clearer what the connection might be. I'm going to write this 100 as 10 squared and the 16 as 4 squared. Now maybe you will see something that looks something like an x squared plus c. Well, maybe not the plus c, but let's just really point it out now. 10 squared is x squared. I highlighted the x squared in red up there when you plug in 10 for x. And then the other term, 4 squared, is x squared when you plug in 4. So there is actually we had to do this in a roundabout way to discover the connection, but there actually is a connection to these problems. This is actually an example of the most important theorem in calculus. So here it is. Let's get on paper, right? So if you have a continuous function on the closed interval a to b, and capital F is any antiderivative of little f, then the definite integral from a to b of your function little f of x dx equals capital F of b minus capital F of a. Make sure that you have a moment to write that theorem down. Um, so we'll see more examples, but I want to point out that this already up here is an example. So let me try to make that as clear as possible, because I know every time there's a new thing, it's like, well, what's going on? This is a continuous function thing. Don't worry about it too much. The only examples we have in this class will be. Um, but the thing is, this capital F is any antiderivative. So one antiderivative is x squared plus 0. The c, remember, is any number. And every time you pick a different c, you get a different antiderivative. So you could have the antiderivative x squared plus 0. That's the one I would use. I would just use the antiderivative where c is 0. But x squared plus 1 is another antiderivative for this problem. X squared plus 2 is another antiderivative. X squared plus 3 is another antiderivative, and so on. So the thing is, you pick an antiderivative, and the most convenient one in this case is just x squared, or x squared plus 0. So you have an antiderivative. So I know technically there's no notation for the indefinite integral here, but since there's talk of antiderivative and the indefinite integral is an antiderivative, that's the connection, right? So that these things really do both appear here, even if this one in this specific notation isn't mentioned. It's said in words by saying antiderivative. So you have this definite integral problem like this one right here, right? So the little a is 4, the little b is 10, the little f of x is, in this example, 2x. Then what does that turn into? It's capital F of b. So take your antiderivative, like I said, x squared could be that antiderivative, and you plug in b in this. So I know it's strange, but we plug in the upper number, this 10, and then after a minus sign, this minus sign, that's copying this minus sign, you plug in a. In our case, a was 4. So you have 4 squared. So it's strange, sure, that it's f of b minus f of a, but it's the thing that works. It's the thing that actually works based on the warm-up problem that we just did. We will look at a couple more examples, right? That's the key thing to do. Before doing so, I want to make sure to I mean, it just said that it's f of b minus f of a, but sometimes people try to do this in like alphabetical order. It's not f of a minus f of b. So 5 minus 2 and 2 minus 5 are different numbers, so you got to be careful for that. If you like or if you prefer this notation, I won't use this notation right away, like not in the first example or two, but you'll see in a little bit. You can write this, and the book writes a notation that looks like this. So you write the function, the capital F function, this antiderivative, and then you write this vertical bar, and you write a b towards the top of it, and an a towards the bottom of it. And writing this vertical pipe and that stuff is notation that just is f of b minus f of a. Capital F of b minus capital F of a. It's just notation, so if you don't like it, you don't have to use it, but you might see me use it on occasion, so I just want you to get used to what it looks like. Um, I You might again go like, well, why is the B above and the A below? Because sometimes there's this thought of like I should start with this one. Well, this B above and A below matches in the integral sign the B above and A below. So just as an example of what this notation really looks like, example, if you had your capital F of x is x squared, that's the one I'm using here, then writing capital F of x vertical bar 10 above 4 below is I can replace the capital F of x, right? Capital F of x can get replaced with x squared. So it could be x squared, then vertical bar 10 above 4 below. And then the whole point here is that based on how this notation is being described, it's you plug in 10 for x. So you have 10 squared instead of x squared, minus, then you plug in 4 for x, so you have 4 squared. Okay, it is just notation, and we will, for now, at least for the first example, not use the notation right away. You will find that the notation is convenient if you use it, but let's try an example where we just do this more directly first. Before looking at the next example, though, are we going to address anything? See if we're doing all right. Okay, so what we did with the warm-up was we used the indefinite and definite integral to lead up to this and discover this thing. We didn't prove the theorem, we're not going to do that, but we're going to just trust this theorem is true and then see an example of applying this. So instead of these two separate problems, I'm going to do what typically happens now is you get this problem, integral 4 to 10. The function here is 3x squared dx. So just as a note, to make sure to connect it back to the generic text inside the theorem box, it's our little f of x is 3x squared. The x value a is 4, and the x value b is 10. To answer this question, we need to find an antiderivative. So this is where it's good to just first look at an indefinite integral. So based on this problem here, we're looking at a new problem. I'm not setting these equal, but the new problem is just remove the 4 and the 10. And this indefinite integral, the result is all possible antiderivatives. And by all possible, I mean that's what this plus c is about. So x cubed plus 0 is an antiderivative, x cubed plus 1 is an antiderivative, x cubed plus 25 is an antiderivative, x cubed plus any number of your choice is an antiderivative. The most convenient one to use probably is this antiderivative, just x cubed plus 0. So a specific antiderivative is capital F of x equals x cubed. Right? So here's a specific antiderivative. It's one of many possible choices. And now we can go back to the original question. What the fundamental theorem of calculus is telling us is that this problem, this definite integral problem, which should be a number in the end, is take this antiderivative, capital F, and plug in 10. Then after a minus sign, take the same antiderivative here, plug in 4. So I wrote this right now as capital F of 10 minus capital F of 4. Now we do this algebra step of plug in 10 into the capital F function, so 10 cubed. Plug in 4 into the capital F function, 4 cubed. 10 cubed minus 4 cubed. You could leave it like this on the final exam for all I care, but I want to just really emphasize that you get 1,000 minus 64, or in other words, 936. So that ends the question, or the answer to the question, but I want to just take a moment to talk about how the fundamental theorem of calculus said you can use an antiderivative, any antiderivative you want. So here's a second answer. You're probably not going to do it this way, so I wouldn't even maybe bother writing this down, but I just want to point out that this is in principle possible. It's allowed. So I'm starting the answer with the antiderivative or the indefinite integral first. I didn't write the first look at this time around but there's just to make compare apples to apples. I'm trying to get that part down first. Okay, and then specific antiderivative. So you can pick for C any number you want to get a specific antiderivative. I just picked 1, 2, 3, 4, 5 for capital C. So you have x, so capital F here is x cubed plus 1, 2, 3, 4, 5. And then when you run through the same rigmarole, you have this, again, capital F of 10 minus capital F of 4. However, right now, the capital F we're using is a little different. It's x cubed plus 1, 2, 3, 4, 5. So what happens when you plug in 10 for x in here, you get 10 cubed plus 1, 2, 3, 4, 5. After the minus sign, since there's two terms, we need parentheses. Be careful here. This would be 4 cubed plus 1, 2, 3, 4, 5. But here's the thing. Once you distribute the minus sign here, the positive 1, 2, 3, 4, 5 and negative 1, 2, 3, 4, 5 cancel anyway, so you're still left with the same number. You're still left with 936. So you can use any antiderivative you want. You know, like, so there's many antiderivatives of 3x squared, and you can use any of them that you want, but probably to save a little writing time, I wouldn't pick C to be 1, 2, 3, 4, 5. You could. You're allowed to. That's what this is trying to show. But it's probably just easiest to use C as 0. So not here. You don't want to put a 0 literally right there. It's just when you pick which antiderivative you're going to work with, you just have x cubed plus 0. So what I'd like to do, we answered this two ways, and you'll see that in the future I'm just going to always pick C to be 0 when we're in this portion of the problem. But on the next slide, I've got here integral 4 to 10, 3x squared dx equals 936. So I would write that down. Um, and I need to say a couple facts about this before we move on to the next problem. First of all, actually, before even that, are there questions? Yeah, just since we completed the process here twice, maybe I should pause first. Are we still finding the area with these? Yeah, that's actually, it's funny you asked the question. This is literally what I want to address on the next slide. So we found the area without ever drawing a picture. How's that? Like this number 936 is actually an area. Ah, it stole my fire. This is exactly the point I wanted to make. That's what the, we found an area without finding an area. I know that sounds sort of silly, but like normally finding areas like, oh, 1/2 base times height and length times width and all these circle area formulas, these kinds of things. And we found an area without doing any of those processes. We found an area a new way, a sort of a clever way, if we could say it that way. So I'll leave it on this slide for another moment, see if there's another question about our process. But yeah, I want to talk about, are we still finding area with these, was the question that was asked in the chat box. And yeah, we are. We just, not in the usual way we find area. We didn't use any area, 1/2 base times height type formula. So here's what we had, right? Integral from 4 to 10 of 3x squared dx equals 936. We are actually going to use this next class meeting. So tomorrow's exam, but I mean on Monday, we're going to use this fact next time. So I would kind of box this, put a star by it. On Monday's class, within the slides, I will mention this again and say, look back to Wednesday's class and notice there was a star by this. We have to use that. It'll help anyway. So here's the other thing. The number that we got here was a whole number, and to me this is a little surprising. This is surprising that we have a whole number because this is actually an area that we computed. In the picture, which you'll see, if you click on this link, I already pulled it up, so let me just drag this other window over here. Here's the picture, right? So the function is 3x squared, and that's shown here in red, right? So this blue region is what the integral represents. This definite integral number was 936. That's the area that's in blue. Here's the thing, there's straight sides, so there's black vertical line. So there's two straight sides like that, up and down. There's the bottom is a straight side, that's the x-axis, but there's the top of this blue curve, this blue region is not straight. It's made from this red parabola. It might look straight, but you can see it's kind of tilted, right? It's concave up. It's got some concavity to it. So even though this is curvy, the literal amount of, literally, not an approximation, the exact amount of area shaded in blue here is 936. That's to me a little shocking. I would have never somehow thought that the area, so we found the area to be 936, right? There's this curvy side. And that's the other thing I wanted to point out, actually. So let me read this bit of text. So we've got this curvy, not straight side, right? So we can't use a triangle area formula, which sometimes people try to do. Sometimes people look at this, they might try to graph it, and kind of where this point 4, 48 is, kind of draw to the right a straight line and say there's a box down at the bottom, and there is a box at the bottom. But then above it, they'll say that, oh, what I have is a triangle, so 1/2 base times height. But this is not a triangle. Not made of 3 straight sides, right? There'd be a straight side across, there'd be the straight side vertically, but then the sort of hypotenuse side isn't straight. So it's not possible to do this one using, standard geometry formulas. The only way to compute this area is actually using the method that we just did, using the fundamental theorem of calculus. Okay, so let's do another one. Definite integral from 3 to 9 of 2 over x dx. So as we do a couple more examples before I have you practice, I'm going to each time point out a different error that people make. I don't just things to just be careful of. So first we need to look at the indefinite integral. Um, what I want to ask you to avoid doing though is this. So this text in red, I put an unhappy face before and after. Sometimes what people do is they'll take the problem that's up here and they'll say that that is equal to the indefinite integral. These are not equal, right? So yes, this problem is the next step, but just put it on its own line, right? So these are not equal because one's a definite integral, one's an indefinite integral. Don't ever say that a definite integral and an indefinite integral are equal, because one of them, the the final answer to this is a number, and the final answer to this one is a function plus c. So instead, just write this integral 2 over x dx on its own line. Just no equal sign connecting this and this. Okay, so I'll do that, and I've just put it on its own bullet here, right? So integral 2 over x dx. Once you bring the 2 in front, you're integrating 1 over x, and that would be ln of absolute value of x plus c. So the point is 2 times ln of absolute value of x plus, pick a number of your choice, any number of your choice, and you'll get an antiderivative that's relevant for this problem. So I just wrote some of them down. I plugged in c as 0, I plugged in c as 1, I plugged in c as 3, 2, 1. Those are all antiderivatives. But I just want to use the one that, so I'm just pointing this out here. I'm not, it's not, you wouldn't normally write this as part of an answer. I'm just in class though right now. It's worth discussing that any of these could work as your capital F. But why not just use the one that's the least amount of writing? Yeah. So the most convenient one to use, the most convenient antiderivative to use is capital F of x equals 2 times ln of absolute value of x without the plus c. So up here, when presenting the indefinite integral, there should be a plus c. When it's time to use a specific antiderivative, I'm going to go with 2 times ln of absolute value of x plus 0. I've plugged in 0 for the c here. Okay, now we can go back to the original question. Okay, to just practice that new notation, you could skip writing this step altogether if you don't like the notation. But this is the antiderivative we've chosen, and then evaluate this at 9 first, and then at 3 next. So the upper number first, and then stick a minus sign in between. So if you don't want to write this, it's just notation for f of 9 minus f of 3. I'm just trying to get you used to it. The more you see it, the more you'll be used to it. And for capital F of 9, well, you just need to plug in 9 into that, right? And then for capital F of 3, just plug in 3 for x into this. So 2 times ln of absolute value of 9 minus 2 times ln of absolute value of 3. And this is the place I would suggest you just, stop for the sake of like the final exam. But I just so that we can talk about what's going on and connect everything all together, I put this into a calculator, and if I didn't make an error as I typed it in, this should be 2.1972. So I'm going to show you another picture, and in this picture, clicking on this new link, I actually already have the tab open. What you'll see is a graph of the function 2 over x and the area under the curve starting at x is 3 and ending at x is 9. And I'll just do this, right? So yeah, there's the red curve. You see it says f of x equals 2 over x. I drew in black x equals 3, x equals 9, those vertical lines. And then I did some fancy thing in this website that allows you to shade in a region. But that blue shaded region right here is 2.1972 square units. Okay, I do have another example and another example, but let's just wait for a moment, see if we're okay, see if there's... Will we end up trying to find the area inside the graph? I'm not sure I quite understand the question. We'll try to we end up trying to find the area inside. Let me put the graph back. You mean like this area in blue we just found, but area inside the graph? Well, so the graph is this thing in red, right? So like on the parabola. Um, so this curve is not a parabola. This one's a hyperbola, but like on. Oh, not this question. You mean the last one? Yeah. Let's just go back to the last picture. Maybe that's so. The area inside the graph. Again, so we found the area under the red parabola from x equals 4 to x equals 10 in the last example. See, the graph is just the thing in red. So I'm not quite sure what inside would mean because it doesn't, the red thing isn't like a circle, so there's not like an inside and an outside. All right, I'll zoom out, but there isn't really an inside to this red curve. If by inside you mean the part above it, well, it goes on forever above, right? You can just keep going up the y-axis. I'm trying to understand the question. Sorry, not trying to be. I mean, area is about like how much paint's it gonna take, right, to cover a region. So that's we used an integral to compute this blue region to be 936. I don't know if it might be easier to just unmute and try to ask or something. Like I'm sort of um, we could.
Never mind. It was a bad question.
Oh,
I
oh,
realize now.
okay, yeah. So, and I hope I wasn't, you know,
Oh no, no.
okay.
I see it.
Okay, yeah, and here's the other thing. We could have changed the x values and computed this little region here instead. There's lots of other things uh, we could compute, but we need, typically you need four things to help trap to create an inside, right? So like it's two vertical lines, the x-axis, and then usually the graph of a function. So, all right, okay, cool. Let's look at another example. If yeah, let's do that. Okay, so again, so each time what I want to do is just kind of point out a different way that sometimes people make an error. So first of all, the question now is definite integral x starts at 2, x ends at 10. The function is 3 to the x dx. So here's another way that sometimes people make an error. So I wrote this in red, is they'll take the original question and then they'll write this equals 3 to the x over ln 3 plus c. However, the thing is that here it's really the same error as the last time, just kind of a different version. It's a different flavor of it. The left side here is a definite integral, and the right side is the result of an indefinite integral. So this is somehow, to me, it's the same error as the previous one of saying that in a definite integral and an indefinite integral are equal. Here, this is just what the indefinite integral would eventually become anyway, right? The way to write this instead is to write since, if you want to even put a word, you don't have to put the word, but the point is if you look at the indefinite integral, so leaving off the 2 and the 10, again, this is not equal to this, so it's just on its own line. Integral sign 3 to the x power dx. Since this is 3 to the x over ln of 3 plus c, that was one of those antiderivative rules. So this was one of those antiderivative rules, just as a reminder, good reminder for tomorrow's exam. This was an integral rule that was developed before we ever had u substitution. So I'm calling that like a pre-substitution integral rule that we had, or an antiderivative rule. So based on this antiderivative rule, the capital F I have in mind is just this part, right? So I didn't write about it as much as in the previous questions, but I'll take the original question up here, and then take my capital F, which is just that part, and plug in 10, and then plug in 3. So here's one way to write about it. The capital F function, I didn't even write a capital F, right? But the capital F function I have in mind is right here. 3 to the x over ln of 3, and then plug in 10 first, plug in 2 next. So you end up with 3 to the 10 over ln 3 minus plug in 2 for the x, so 3 to the 2 over ln of 3. I went ahead and plugged that into a calculator, and it's 53,000. That's huge. Again, not expecting people to plug into a calculator like this. I think by having the number, it makes it much easier to talk about what it is this does. So I'm sorry to show you another picture. I'm just trying to reinforce what's really happening here. So we're taking the graph of this exponential function. Exponential functions are huge, right? Like this is how you model well things like disease spread actually. Um, and this has a very curvy side, right? This is very bowed, very concave up. And this blue region here, I had to change the axes up. You'll notice that there's some shenanigans. The y-axis, sorry, excuse me, the x-axis starts at like -4 or something and ends at 15, whereas the y-axis, I shrunk it down so that you could see it. Starts at like negative 1,000 and ends at positive 60,000. I scroll out just a little bit more. So this blue region, it looks so tiny, but it's not. It's just I just had to like squash the y-axis down so that we could really see things in the picture. So this blue region here, it really is 53,000 square units. Okay, I'll do one more, and maybe not point out the same error this time, maybe just a different kind of error. So, and maybe later, right? So let's look at integral 1 to 4, 6x minus 5 dx. So here, um, now let's just dig into this. Is what I think a first step looks like. If you want, write indef as a shortening of indefinite integral. I somehow for me, just even writing that is the thing that's preventing me from accidentally saying that this thingy up here is equal to that thingy, because they're not equal, right? So they're related. One, now that we have this new thing today, the fundamental theorem of calculus, we now finally see that they're related. They're related, but they're not equal. Okay, so here, find an antiderivative. So uh, 3x squared minus 5x plus c, don't forget the plus c here, but when we apply the fundamental theorem of calculus, we go back to the original question, and then I like the most convenient antiderivative is the one that doesn't have a plus c, or rather, it has a plus c, it's just you plug in c as 0. So we take this antiderivative. The thing circled here is the specific antiderivative when you plug in c as 0. That's what's written here. And we're going to plug in x is 4 and then plug in x is 1. So I'm trying to be careful with my words, right? Because plug in, there's an x and there's a c. So when you plug in c is 0, you get what's underlined here. And now with what's underlined there, we're going to plug in x is 4 and then plug in x is 1. So it looks like that. To plug in x is 4 first and then plug in x is 1 next. And again, I would just, to be honest, in terms of final exam type stuff, just leave it like that. Why bother simplifying? But I just want to point out here, I just ran that through a calculator. I don't want to even bother with any arithmetic error myself here right now. That number's 30. And the point I want to make is be sure to plug in the 4 first and then the 1 next. Sometimes what happens is people switch it. So I try to use square brackets to help clarify, but sometimes people write this one first and then do you see how these are swapped? So this and that one. Swapping them is a mistake. That's the swapped version is what's shown in red. So if you do that, you'll end up with -30 as a final answer accidentally. So this should be positive 30. We'll look at a picture of this one. So if you click on that link, the graph is now y equals 6x minus 5. And that's actually, well, that's a y equals mx plus b, isn't it? This red line. Line of slope 6. Y-intercept is -5. So the region here in blue, we computed this by looking at antiderivatives, by using the fundamental theorem of calculus. That's totally fine. But now this particular shape has 4 straight sides. So we could have instead used area formulas, right? We could have thought of this as, cut this, and there's a tiny little rectangle at the bottom and a big triangle above, and we could have used area formulas, right? The point is, the way we solved this problem up here was we applied the fundamental theorem of calculus. But because the region shown in blue in this one has straight lines, the other examples we've looked at today don't. We could have done this using geometric area formulas, so using yesterday's method. Okay, so let's take a little time anyway. Maybe not enough. Just want you to get your feet wet. Just try at least one of these, and then I don't think there'll be quite enough time to get all the way through, but uh, give it a try, and then let's see. There's 15 minutes left, so I want to like do like let's say 10-ish minutes, maybe 8-ish minutes, and then I want to end on a slide that kind of summarizes and clarifies some things, and then do announcements. I just saw a question come in. What were the last two? You mean how to do these last two? Perhaps. I'm gonna. Okay, yeah. Again, without setting equal, right? Um, this first, so not equal sign, not an equal sign here, just kind of a little off to the side. First action would be to leave off the 4 and the 9, so to look at the indefinite integral problem. So the antiderivative, the indefinite integral or the antiderivative problem. So this, and so then here one term at a time, take an antiderivative, right? So 3 to the x, its antiderivative is 3 to the x over ln of 3 plus, and then 1 over x, its antiderivative is ln of absolute value of x plus c. So now that we have the antiderivative in place, we can now go back and answer this question. Right? So I know we do this work first, but then we can actually put an equal sign here and say that this is going to be plug into. I wish I had easy access to colors here. I don't know if this is going to work. This is not a good idea. I'm sorry. I'm just gonna. So let me maybe box that part because I just want to now plug in capital C is 0 for the specific antiderivative I use and have here. Let's see. So 3 to the 9 over ln 3 plus ln absolute value of 9. Okay, so that's the part before the minus sign, and the part after the minus sign would be 3 to the 4 over ln of 3 plus ln absolute value of 4. That'll end that one. This last one here, again without an equal sign off to the side, we first have here integral without the 2 and the 3, x to the fourth x plus 8 dx, and that this is not going to be a U substitution one. I think this one, it will make more sense to first just rewrite this one using algebra as x to the fifth plus 8x to the fourth dx. Right? And then, yeah, so a little algebra first before anti-differentiating, and now an antiderivative one term at a time. X to the 6 over 6 plus 8x to the fifth over a 5 plus c. Then we'll take this antiderivative and apply this over here. So then plug in 3. So 3 to the 6 over 3 plus 8 times 3 to the 5th. Oh, geez, why is this erasing? Okay. 8 times 3 to the 5th over 3. Then same deal. I'm sorry about this pen. Okay, there we go. Minus, getting myself lost. Okay, then plug in 2. Yeah, plug in this 2. So 2 to the 6th over 6 plus 8 times 2 to the 5th over 5. Sorry for how messy this is written. I was really fast. I'm sorry about that. I just wanted to. I'm close to that 5 minute mark, and I wanted to, right around that 5 minute mark, I wanted to summarize some things, try to clear up things where people tend to get confused on some of this. So I want to, yeah. So again, that was really rushed, and I'm sorry about that. What I intend to do, I haven't even uploaded the slides yet. I'm going to do this right after we're done meeting. I just was so maxed out time-wise of things yesterday. But I did, when creating these slides, I created a link. This link doesn't work yet. It's not going to matter for tomorrow's exam, none of the, but like, this link is going to go to a PDF once I just make it this weekend, and then you'll see what handwritten solutions look like. Because I think sometimes the slide-based solutions make it a little like it's nice on some level, but I want you to see more like what typical handwritten solutions look like. So I'm going to handwrite something and then make a PDF, and then that was what this link is going to go to. So you'll see that later. Sorry, I haven't gotten around to it yet. What I want to do though, before ending class, is do a little announcement. This is meant to help not only for the future, like as in for the final, but also I want to clarify so that there's no confusion for the exam. So just kind of please stay tuned for this and then for the announcement. So we have this definite integral. When you're given a definite integral problem, you've got choices. Either method one, you do this as an area problem. That's what we did before today, right? We treated it like a signed area problem. And in fact, I just want to point out, if you're looking at a problem that looks like this, and you'll have to get used to it. So I can't say a whole lot right now, other than if you're looking like integral negative 3 to 3 of root 9 minus x squared dx, that's a half circle. And the only so then that final answer to this one, this is actually equal to that number right there. That's the only way I know of how to do this. And so like let's actually do know another way, but we're not covering it this semester, right? So the point is the only way for us to do this problem is to interpret this as an area. Same deal. If the integral has absolute values in it, the only like we don't have any antiderivative, like you don't differentiate something and then magically absolute values pop up, right? So when you see like this, this is this V shape, and think about like the creation of two triangles. So interpret as a signed area. There's two situations when you have to, and then there's other situations where you might want to. Like if you know that the function is a straight line, maybe you want to just draw a picture. Your call. Um, the other method to do this, if you have a definite integral, is to look at the indefinite integral first, as we've been doing in our examples today, find an antiderivative, and then apply FTC, meaning fundamental theorem of calculus. Now, the discussion that we're about to have here, how to find antiderivative, these are the comments I want to really make right here. This is the exam for let's get our minds on these techniques right now. Things I want to say are to find that antiderivative. Even here, there's methods. So within method 2 for a definite integral, if you go about finding an antiderivative, and all this comment is relevant for exam 4, to find an antiderivative, sometimes you have to use an antiderivative rule that came before we ever looked at substitution. So I listed some of them here, or try to list as many, at least the popular ones, right? So the antiderivative rule that undoes the power rule. So that's you raise the exponent by 1, and then you have to divide by the new exponent with a plus c. These are the three I think most common anti-differentiation rules we had before we ever had substitution as a method. Also, you might need to find an antiderivative by first taking the problem and using algebra first. That's in fact in the one you just asked about. I remember we had to distribute, wasn't it x to the fourth? I think we distributed an x to the fourth. Did a little algebra before anti-differentiating. So sometimes that happens. And then, of course, there is substitution as a method, but it's not the only one. It's not even my go-to. It's like, substitution's a lot of work. So if I can get away with just foiling or distributing and then find an antiderivative, I'd rather do that. So these comments are very relevant for exam 4. Again, exam 4, just to clarify, does not have definite integrals. So definite integrals, whether by signed area or by fundamental theorem of calculus, doesn't happen. Not on exam 4. Exam 4 does have indefinite integrals. So indefinite integrals are about finding antiderivatives. So these comments where the triangular bullets are, those apply for exam 4. Just as a round of announcements, today is Wednesday. Please complete that pre-exam math as a process assignment, meant to be super quick. Just allows you to kind of focus on what problem types there are on the test. And then since Thursday is the official date of the exam, we will not meet for class live tomorrow morning. You can use any 5-hour time period on Thursday or Friday to complete the exam. And please turn in a single file, one PDF file. And I would strongly suggest still keeping current with web work. So that'd be number 41 for today. All right. Thank you all. Sorry for going slightly over.